So I'll start with the presentation, but we will shift over to the notebooks and then again come back to the presentation in the end. So today we are discussing BERT. Now this was a milestone uh, technology, and this was developed by Google. Now, after Google developed this technology, Google does not realize how important a technology they have developed, and that is the reason they shelved it. And instead, Google paid attention to its enhanced search engine, um, which Google's original search engine, which Larry King got his PhD for, was called the PageRank algorithm. Now, based on PageRank algorithm, actually Larry King made the Google search engine. That was his PhD thesis. But then it underwent a major overhaul somewhere around about 2016, 2017, and they had a new algorithm which is called Rank Brain, and that is what Google uses for search engine today, Rank Brain. But before Rank Brain, Google had actually invented BERT technology. Now this BERT technology, Google said that it's okay, it can do semantic searching and all this kind of stuff, but let us shelve it, and they did that. And as a result of which, actually, this technology was also developed because of a paper written by Indian. I forget his name, but you can search for the paper called "Attention is All You Need." So, it's a very important paper in the life of large language models. So, actually, everything about large language models started from that paper. It's called "Attention is All You Need." Now, from that paper, they developed this BERT technology, and the main thing what we will look at today is that what is this attention mechanism? The attention mechanism is the whole heart of LLMs. Okay, so we will have a first look at that. And second thing is that this entire thing, BERT, is basically a transformer. The T in BERT stands for transformer. So we will have a first look at transformers, and transformers are the driving force behind LLMs. Okay, it is only the transformers which have been modified, and the modified versions is what we know as Gen AI. So Gen AI is the hierarchy is basically AI. Under AI we have ML. Under ML we have DL, deep learning. Under deep learning we have transformers, and under transformers we have Gen AI. So we will look at two important things today. One is the attention mechanism, and one is the transformers. And because Google didn't pay attention to BERT, just in 2 years' time, Google invented BERT in 2016. In 2018, OpenAI came up with this GPT model, and by 2019, GPT had caught on the imagination of the people. And by 2020, every individual means earlier what was the domain of computer scientists and programmers and organizations became a domain of every individual, every citizen. Everybody started using ChatGPT, and then Google sat up and said that we should have exploited BERT better. So they enhanced that, and they enhanced that into Gemini. And all this time, Gemini is basically playing catch up with OpenAI. Now there is a new player called Claude, and though OpenAI is still ahead of them, but so now it's basically a three-way battle between Gemini, Claude, and OpenAI. Others are there, like Microsoft is there, or Oracle is there, and things like that, but their products are not so. Even Amazon, for that matter, but their products have not caught the imagination of the people. So it's basically a war between OpenAI, Claude, and Gemini. All are equally good, but in between, somewhere in the beginning of 2026, I felt Gemini was much better. But Gemini has a lot of tools actually, Notebook LM and this thing, that thing, and all that kind of stuff. But then ChatGPT has modified, and right now the current version, 5.5, is far superior to Gemini. So if you are experimenting with different ones, you can try it and you can have your opinion. Anyway, let's get on to the content. So last time we basically saw that using Elmo we could solve the polysemy problem. So Elmo helped us make do different embeddings for the word bank, and we could do that for any number of words where there is a differential meaning. Now we will continue with the same problem, but the thing was that what was happening was that Elmo learning was learning using a neural network. So we know that it has got a CNN and two LSTMs. But then what is happening is that even after having LSTM, where memory is what do you call saved, and memory is used, but the memory is still limited because it cannot utilize very far flung memory. So only the nearby memory has real contextual meaning in Elmo. And second thing is that the search is happening in unidirectional. Though I have a bidirectional stuff, that is, I one round I go in the forward direction, and then I come back. But I am doing that individually. I'm doing that run in one direction first, and then coming back on the second direction. So we will replace this whole stuff with BERT, in which what we will do is that first of all, I'm not going to be checking word by word. I'm going to use the attention mechanism, and I'm going to use a transformer where I will search for context in parallel. So across the entire corpus, what I've got, I will search for context in parallel. That is where the attention mechanism fits in, and then the transformer basically tells me that I'm going to be searching parallelly. So I'm going to be doing the parallel searching using the neural network in both directions simultaneously. So we will see how that happens. So here I don't have a problem of memory decay or anything like that, and so it is superior, but we will let us check whether it's actually superior or not. So with that context, I will take you down to the notebook first, and then we will come back to the presentation once again. Right? Any questions so far? Thank you. Yeah, okay, no questions. Done. So I'm in the notebook right now. As usual, what I'll do is that since we are learning from the first principle, I will first create the forward pass. And after creating the forward pass, after understanding how the forward pass happens, then I will create the complete neural network. And after we have inspected the neural network and understood it, then we will apply it in a practical problem and see whether it works or not. Right? So just 1 minute. Okay, so let's start. So I load the libraries as usual. And this is just a function which I require for display. Okay, now I take a sentence just like we have done in the previous thing also. And most important thing is that, look here, I extract the tokens, that's okay, but I'm adding some special tokens. So these special tokens are required in BERT for indicating, like for this token indicates the beginning of the sentence, and this token indicates the end of the sentence. So this is something which I'm adding. So we will have some special tokens in BERT, right? So that is number one change what we are going to make. Second thing is that I have defined something as number of heads. So what I'm doing is that I'm making an embedding of size 4. So this is the model which I'm making. And since I'm making a size 4, so I'm taking 2 heads. Now what exactly the heads means, I will show you. So these are the main difference what you can immediately see as compared to what we were discussing in Elmo. Now we will start making the model. Now see here, I am not making a single embedding here. Instead, I'm making 3 embeddings. I'm making a token embedding, that is at random. I'm selecting some numbers right now, and then I'm making a position embedding, and I'm making a segment embedding. So each of them have got their own significance. Position basically deals with the position of tokens. Token embeddings, you understand that embedding for the token. Position embedding is the position of the tokens in the whole corpus. That also I'm making into embedding. And the segment, in this case, the segment is basically a sentence. So even for that segment, I'm making a embedding. So I'm making three embeddings. So this is the another difference as compared to all that we have discussed so far. And then what I'm doing is that, okay, I'm sure I'm taking the columns and all that. Then I'm going to be, I'm just displaying the embeddings to you at this stage. So let us see how they look like. These are all random numbers. So, but anyway, for the entire set of words, what I have got these three embeddings: token embedding, position embedding, and segment embedding. Okay. So then what I do is that after creating these three embeddings, I add up all the three embeddings. Okay, I add up all the three embeddings, and I'm making a word embedding of 4 dimensions. So that's why I have got 4 columns of embeddings here. This has been transposed. So it is basically the 4. I'm calling these 4 columns of embeddings as 4 heads: H1, H2, H3, H4. We will soon see what is the requirement for that. So I've made these 4 heads. So basically, this one column is the embeddings. Sorry, this one row is the embedding for each word, and that is the 4-dimension space which I'm creating right now. So for each word, I have got one row of 4 columns, 4 elements, which is the embedding. Then what I do is that I project these embeddings into something called QKV. Now this is the main component of the attention mechanism, where I have three components. One is called the Q. Q is the query. K is the V is the value. Now you have to understand what is the purpose of this. So this, you will notice here, I have given it here. Yes, Deva, question.
Before we move on, so with respect to the position embedding, my understanding position was where exactly in that particular corpus the word token represents. Like for example, where exactly the bank token is in that particular sentence. That was a position I was thinking. But here, if you see, it is started with the random values for each of the position. So I was just a little confused whether the position embedding is really the position of the in that sentence.
Just hold on. Just hang on for some time. I just hang on till I train the complete network. Then the position embeddings meaning will become clear to you.
Okay. Thank you.
Just hang on. I have to find a way to train it, right? So for the training that, I require a mechanism. So I will show you what is the mechanism I will use, and then the position embedding will become clear to you. Right. So now let's understand this QKV. The Q is the query. The query, basically what its purpose is that it is trying to figure out what a word is looking for in the rest of the sentences. Rest of the sentence. The sentence is our corpus right now. So with respect to that corpus, so what is the word looking for in the rest of the sentence is what the query indicates. And the key indicates what that word offers to the other words. So we are trying to figure that out. Now this QK is very important. QKB is very important. So basically what you'll be doing is that using the QK, you'll be finding the value, and the value is what will be passed on as a context of the particular token in the LLM. So once it has a context in the LLM, then the LLM can use the token for any purpose, either for understanding the input or for generating the output. So that's why this QKB is governed by this formula: softmax of Q into K to the K transpose divided by DK. DK is the dimension, and multiplied with the value. So this is the formula. I will discuss this in more details when we actually start the transformer classes. So right now, just have a what do you call, have it in the back of the mind that this is a very, very, very important topic in the whole thing that we are discussing. So once we have this QKV defined, and we will project our embeddings what we generated. So this initially I have generated all the embeddings as at random. So now I will project these embeddings what I've generated, the final input embedding which I got. by creating this token, position, and segment embedding. So I added them up. So I got this. So now I will project these embeddings onto the QKV. So Q, K, and V. How do I project? I'm basically taking these weights as at random. You can see that I have assigned random values to this particular weight, and this D model is basically 4. So and then I will do a dot product. So I will show you. I will do a dot product. Where is the, right now? I have only I only displaying the values of this variables which I created. So these are the random values which I've created. And after I create these random values, you see here I'm taking the dot product of my input onto these 3 things, that is query, key, and value. So I do that, and I will show you the output what I get. So I am getting for each word now the query matrix, the key matrix, and the value matrix. Okay. Now you see here, I have broken this down into 4. I said my D model is 4, so that's why I have got 4 elements in the matrix for every single token or every single word in our case right now. So that is what I have done here. Now what I do is that, okay, this is just, I'm showing you the QKV for one individual token, that is for bank, the input embedding is like this, and the QKV is like this. Now what I do is that I break this into 2 heads. I say that I will use 2 heads. So I don't do it at random. So what I'll do is that I will take H1, H2 as one head and H3, H4 as one head. So I'm breaking into 2 heads. So 4 divided by 2 is 2. So I will take 2 columns. I'm not doing it at random. That sentence is very important. I'm doing it absolutely in a predictable manner, in a deterministic manner. Okay. So I break it into 2 heads. So I'm splitting the entire stuff. So now you see that in head 1, I have got the QKV, only H1 and H2. So this is QKV on head 1. And on head 2, I've got this QKV, that is H1, H3 and H1. Now, why did I break this into heads? Because each head will look at the entire corpus from a different perspective. Okay, that is why. And it will do that in parallel. So now just verifying the shapes. So I get this. So now what I do is that I create a dot product, and then I do a softmax like the formula I just showed you. So each head will produce an output. So you see that for head 1, I got this attention score for every token what I have by doing this dot product and then doing the softmax. And for I got the this is before the softmax, and this is after the softmax. So I'm getting a probability. So and then after taking the attention weights, I basically get an output from each head. So this is the output from head 1, and this is the output from head 2. Okay. Now what I do is that after having calculated these heads are basically trying to find some unique stuff in about the individual words from the corpus what I have given them, right? Then after each individual head has done its work, I put them back together. So I put them back together. Now it's back to a single output. For every token, I have got the single output. After now, what I do is that after I get the single output, then these numbers, they become all over the place. So I do a normalization. Normalization, you understand that I will basically, if I try to bring it back to a single, very, very close range of numbers. So I do the normalization. After normalization, what I do is that after these are currently the embeddings what I have received right now. I will put these embeddings through a feed-forward network, a neural network. I will put this in the feed-forward network where I will initially assign weights at random, W1 and W2, and bias B1 and B2, and I will assign them at random, and then I will basically do this. That is, this is the embeddings which I got right now. These are the embeddings which I got right now. I will do I'm calling this Z into dot product with weight 1 and plus the bias B1, and I will do this output. What I get from here, this is the feed forward hidden output. I will do this output into weight 2 plus bias 2. So it's a two stage neural network. So that's very easy to understand. So once I do that, this is what I get as the current state of the embeddings for each individual words. So what I did was I broke into into attention heads and tried to collect some meaning regarding the words in the attention head. Then I put them back together, did a normalization, and then I fed it through a feed forward network. Right. After feeding it through a feed forward network, again I do a normalization. So this is again bringing the values back to similar range. This is required in every neural network actually. And after I've done that, what I do is that I have got my final output. These are the final embeddings. So what I can do is I can figure out into individual tokens, what was the importance given by each head. So you see that head one with for the embedding for the word bank, give importance to the word withdraw, then separator. This is just a random number. When I train it to a neural network, you notice that each head will pay attention to a certain word. Now you can notice here something very significant. The thing is that the first head is paying attention to withdraw. That is, it is paying attention to the word withdraw. And the second head is paying attention to the word went. So this must make it clear to you that each head will focus on a different aspect of the meaning associated with every individual token. So are you able to get this from the demonstration which I'm giving you right now? The importance of the attention head?
Yes, Partha. So my understanding is like here each attention head, the head 1, head 2, it takes the bank, and for the bank, how does the other words relate to closely?
Yes.
Yeah. So that's what it does.
So actually, in real case, what happens is that supposing you are entering a input into a LLM like ChatGPT. So you enter a long input, and then what ChatGPT will do is that for every piece of token, what it extracts from your input, it will attach different number of heads, maybe 100 heads, 200 heads, and so on. So, and every head will find a different context for the individual tokens, right? And then after every head finds a individual finds a unique context for individual tokens, then we will put the heads together, and then that combined stuff what I get is the actual context what the LLM will find about the individual tokens. That is why it is able to understand a word from different perspective, because it is attaching multiple heads on each token. Let me use the word instead of getting confused with token, but actually it is token. But here, since we are demonstrating in terms of words, so that is easier to understand. So every word I'm attaching multiple heads on that, and each head is finding a different meaning of the word by scanning its surroundings. So you got the purpose of why I require the attention head, and do you think it is useful?
Yes, I got the concept, Partha. Yeah.
Okay. Praveen, are you okay?
Yes, sir.
Okay. Yeah. Now the thing is that we have established a method for finding the context, but then we must find a way to train the model also, right? So there are many ways. So I have taken one particular way, but there are many ways. So how I'm going to train the model is that I am taking the same input, but I am hiding one particular word from it. Okay, I'm giving it a special name called mask. I'm hiding this. Okay. After hiding this, what I'm going to tell in the neural network is that you find out what should be the value of the word mask based on the context you have understood from the different heads. Okay. If I can train this neural network effectively, and if you can identify this word correctly, then the machine would have learned about the input in a fair way. Do you get the strategy?
Yes, sir.
Yes.
Okay. So in reality, what they will do is that I'm using just one mask, but in reality, they will use multiple masks. So there will be intense training. And if he can extract all the masks properly, then he would have understood what is the meaning hidden inside each word in the particular corpus what has been given to him. So I do that. So now this is random. So it says that, okay, fine, the probability that the mask is I is very high, but you have already experienced that basically once you do the complete training, it should get the correct sentence. Right now, everything is random, so he's just generating whatever the first pass is giving him. Okay, so that is the whole idea. So what we have done is that this is the neural network what we have created. So I will just show it to you. So just recall now. I took my input tokens. I first tokenized. I got the input tokens, and I attached the special tokens. After that, I made an initial embedding, which was at random. So I made three embeddings, that is token, position, and segment, and I added them up together to form a output. And then I initialized the projections, that is QKV, query, key, and value, and then I projected my input onto each of the tokens, that is query, key, and value. Then I split the output into two heads, and now in this case two heads. In reality there'll be hundreds of heads. Okay, and then each head I did a dot product so that it finds this dot product will produce a different output, right? Because the matrices are different. So from that output, what the intention is that by doing a dot product with these individual heads, it will find different meanings in the tokens, in the words which I have given him. Then I put together the heads into one, and I projected it on an output which was also initialized at random. These are weights. I initialized at random, then I normalized it. After normalizing it, I pass it through a feed-forward network. In the feed-forward network, basically, I'm trying to find the weights, which is right now randomly assigned, weights and biases. And then after I do a dot product there, I do a training there. I basically I do a layer normalization once again. And then after getting an initial embedding for the word, for the words, okay, tokens actually, what I'll do is that I'll feed it to a mask language modeling head, and I will continue this loop of training forward and backward till this mask language is able to generate the correct word as replacement for the mask. So this is the whole strategy of training this neural network. Do you understand? Any questions?
Okay. So the prediction head is what I think would be our loss function, where we try to say, okay, this is what's supposed to be mask value, but if you're predicted wrong, go back and retrain. That's my understanding, correct?
Exactly. Very good. My loss function basically becomes whether the mask is guessed correctly or not. That becomes my loss function. Okay. So once you've got this, so now let me show you the complete training. So I again start from here. I initialize my libraries. I get my vocabulary. So you see, I will have many number of special tokens in case of BERT. And actually, the question what you had asked last week regarding why am I not using advanced tokenizers? So BERT actually uses sentence-piece tokenizer, which I will show you when I'm going to the practical example. Right now, I'm just using an ordinary tokenizer just for demonstration purpose. Okay. So now what I do is that I have set my origin token and the termination token, and I set up my mask token also. So here I'm tokenizing. I'm just creating a special token called mask, and I'm masking the word bank. So this is my target word. So this is the basis of my training the neural network. So I set up my whole stuff, and then I'm going to use two heads, and I'm going to make a embedding of size 8. So this is, and then I'm going to use a feed forward network of 16 neurons and 500 epochs and all that kind of. So this you understand. So I'm just setting up my hyperparameters, and then I make my BERT. So that entire feed forward network, what I showed you, that is exactly what is programmed here. So so I just create this, and then I will train my model. So I set up and I train. This is just a pause to show what are the individual probabilities before the training starts. So now here I'm starting the training. So I will train it. So it has gone through the training, and after the training, let's see whether it learned or not. So it indicates that it has learned. Or I could have stopped at 100 also. And now what I do is that let us check whether it is learned properly or not. So now you see that my target word was bank, and the mask has been predicted as bank. And see the probability which it is predicted is nearly 99.9% probability that bank should be the word replacing the mask. And you see the remaining probability. This is softmax, right? So it will give a probability to all the possibilities. So here, see they're so small probabilities. So the amount of confidence it has got in predicting that the word bank is a replacement for the mask is very, very high. Okay. So let us see the embeddings what is created for a mask, and this embedding should be very close to the embedding for bank. That's why it says that bank should be the replacement. So do you understand? Any questions? Last thing, let us see what is the attention it is given. So you see that it gave attention to the word money. It gave to but 26%. It gave attention to the word went, 24%. Okay. Does it make sense? Is it working properly?
Yeah. So this is using both the head 1 and head 2, or
yeah, this is the summation of the attention what it has given. I'm not showing the individual attentions here. Did you get the way I'm training this network? And are you impressed by the way Google has done it?
yes. One question on the input data, Partha. So if you look at our input was just a one sentence, right? The input was almost like maybe 10 words here, or 10 tokens is what we input. But if the amount of, if I want to train this using the book 1, book 2 kind of things, will the input also increases? How do they manage it? Because the matrix will also increase, right? The number of rows increases. How the memory management happens? Any idea?
Yeah. What do you call it? The input is always going to be huge. That's why, see the basic problem why you and I cannot set up a company like OpenAI is that to train a model, the initial cost upfront for hardware, software, everything put together is around about 10 billion. Okay. So why is it 10 billion? Because that is the amount of resources what you require. You understand the software doesn't require resources, but actually what are the resources required is the hardware. So because I'm training such a huge model, That is why I require enormous amount of hardware to do the training. And that is a major barrier why everybody cannot set up a company. Though I understand the technology, but everyone cannot set up a company and start doing business with this, right? Does it answer your question?
Yeah. So I yes. So I was referring in YouTube some things. So this is what I understood. So when they had a huge data, so when they do a tokenization, right? So I think if I'm correct in GPT-1 or GPT-2, they did only for 50,000 tokens, and then they went to 100,000 tokens in the next version. So that way they increased. So my understanding is this. So when I take, say, for example, I take a books related to Shakespeare or children books, something like that. So I have 100 books with me. So I feed all the 100 books to tokenize this. This could result in, say, 1 million tokens. So assuming that I ran BPE or sentence piece or word piece tokenization, I get this 100 tokens. So then I need to make sure that this 100 tokens encoding is what I need to do with 100, say, 1 million into whatever the embedding size I wanted to. That would be a big embedding size, right? That is what my embedding matrix would look like.
Correct. Correct. See, the thing is that what I am telling a lot of people, I'm trying to convince them is that, see, it is not a matter of joke, like I just told you, that though I know the technology, how to make LLM, I can actually create a LLM and do business with that. But then what is possible definitely for me is that instead of creating a LLM, I can create a small language model. Just like you said, you got 100 books. But what if I take very focused data, like let's say, for example, you're a steel company or you're a oil and gas company or you are a telecom company. Now you want to make a language model which will talk only about telecom, right? So now if you gather all the information regarding telecom, which should be a much smaller corpus as compared to a general purpose corpus. So if you take that much smaller corpus of just telecom knowledge and create a language model based on that, so that language model will be something much smaller, very much smaller as compared to a language model like GPT or something like that, or BART or something like that. So and then it becomes feasible for you to create a business around that SLM, which is a much smaller model, because you will have you should have enough amount of money to be able to invest to create that SLM. And then that SLM can become the backbone of your company's knowledge bank, because you are a niche company, you are in a niche domain, and you only require the niche amount of information regarding how to what do you call, help your people understand different things when they have a query to ask. Now, see, in this particular way, there are many advantages. First of all, you will not utilize huge amount of money of your organization in buying licenses from these vendors like OpenAI or Claude or whatever. You can save a huge amount of money from that. Second thing is that since the technology is now in the open, you can apply it effectively and create a SLM, and that will 100% serve the purpose of your company, because you are in that domain only. If not 100%, at least 70% to 80% of your job will be of knowledge management will be done through that tool, and you have total control of the tool. You don't need to pay any license for that. And once LLM is prepared, if you since this is SLM, so the underlying knowledge bank on which this SLM is trained will not change too much. And even if it changes, you can always add it by using, which we'll discuss later on, by using technologies like RAG, etc. So I need not have to train the model once again. I can augment the knowledge data, and it will automatically be able to take advantage of that. And so if 80% of your job of knowledge management can be done through the SLM, and then only 20% of the job remains. For that 20% of the job, the number of licenses of tools like GPT or Gemini or Claude, which you have to purchase, is much lesser, much less than as compared to having a general purpose tool for all activities of your organization. So think about it from a CTO point of view. That don't you think this will what do you call be a win-win, because you are having all the knowledge what you require for your employees. At the same point of time, your expenditure is a fraction of what you would have been doing. Does it make sense?
Yes, Partha, it does make sense. Yeah.
Okay. Praveen, do you have any questions?
No.
Okay, good. So now let's make an application out of this. So this application is Hindi news search. So I will put the search in Hindi, but I will search through English news items. So let us see whether it works or not. I will query in Hindi, but the output I will be searching through English news. So it is a cross language activity. So let's see if it works. So now, you see here now I'm using tokenizer sentence piece. Where is that? This is a sentence transformer, not this. I will show you I'm using sentence piece as a tokenizer. Just 1 minute. It's loading the libraries. Taking some time. Okay, done. So these are the feeds. I'm going to take it from Hindustan Times. They are freely available. You can add to this knowledge bank by taking more feeds also. So now I have got these different articles from Hindustan Times, which is my corpus. So I use my sentence transformer. It's a transformer which I'm taken from Hugging Face. So I got it, and I create the embeddings for my documents. So here actually I have used sentence piece. I have explicitly, I should have mentioned it, but anyway. So I'm creating my embeddings now for the documents which I've got in my corpus, using the BERT transformer. So document embeddings have been made, and the embeddings are of size 384. So there are 285 documents. Now what I do is that I create a function to search. So this is my function to search. Now you see here, I'm giving my queries in Hindi, and I'm expecting that the search will produce English news articles which are having meaningful connection to this query. So let's do that. Okay, now let's analyze. The first query was Kritrim Buddhimata. In case I don't understand, Kritrim Buddhimata basically means AI and Nai technique. So you see the news article which is fetched is AI is distorting practically everything in the economy and challenging comforting. So do you think it is working? What do you say? You want to see about politics? So you see, I said Bharat ki Rajniti, and it's got Bengal elections into place. What do you say?
So the translation is happening by which? Is it by your model or is it?
It is not translating at all.
Okay.
Not translating at all. It is
Oh.
basically finding embeddings for these words, right? And these embeddings, it is matching with the English embeddings of the words. Now it so happens that the embedding for the words like Kritim Buddhimata, it is very close to the embeddings for AI. That is why it is matching this. It is not translating at all.
Okay. Okay.
It's all working on embeddings only right now. Got it?
Yes.
So, so one more question, Partha. So the query that you are saying, you said it will be embedding, right? So, will the embeddings that we used, position embedding, and then the segmentation embedding, and then all the things will be done for even the query before giving it to the model to search, or is it
Yes.
simple?
No.
Same pre-processing will be done.
Same pre-processing will be done.
Okay. But that would be a random generated again, because
I have to start from some point, right? See, what I'm doing here is that I'm generating at random, right? But actually, so my initializations technique is that start with some random numbers and then apply the neural network over the training. It will find the right embeddings. That is my strategy. But then, what do you call? If it's a really large model which I'm going to train, this is not a very good technique. So there are advanced mathematics by which I can get the most suitable initialization point instead of just using a random point. That is also available.
Also, if you look at initially, you passed your documents to the model to create the document embeddings, right? So you got the embedding for your documents. Now, with using that embedding, now you started querying with your Hindi words, right? So this Hindi words, who is creating that embedding for those Hindi words?
No, the Hindi words embeddings are also created from the training only. So let me show you. This search function, you see. See here, the query embeddings I'm creating there.
Okay, you will be using the same model encode option. Okay.
Same model to create embeddings.
So whatever the model encode used to do for our input documents, the way it used to generate the initial input embeddings using position and stuff, it will do the same thing for the query one. Okay.
Yes. Okay. After doing that, then I'm doing the cosine similarity between the query embedding and the document embeddings. See, I'm not translating anywhere.
Understood. Okay.
Right. So this was a breakthrough technology actually. And like I told you the history, Google didn't realize its importance. Nevertheless, they are doing well now and they are deep into Gen AI market. So I've shown you all this. So this was the network what we created, and these are the embeddings which we created and summed them up, and then we trained over this. And I told you about the QKV, so you understand that a little better now. We will discuss this a lot, and this is a very huge thing when I'm going to make a LLM, because this is not only important conceptually, but it is also important in the sense that it requires a huge amount of memory. So there will be a lot of trade-off, like how much memory should I give here? What will be the trade-off if I do not give enough and all that kind of stuff. There's a lot of discussion we will have around QKV. So with this we will do it in the future. And then I showed you practically that how it is finding attentions to different parts of the words and drawing attention from signals which are very prominent. Like it is not giving too much attention to the word to, the, and all that kind of stuff. I did not remove any of the things, right? Everything was kept intact, but it is not paying attention to that. But it is able to pay attention to the important word like withdraw or money, and you saw how the mechanism worked, right?
Yes.
Yes, Partha.
Yeah. So in our case, what we were doing was that the head one was finding semantics and the head two was finding grammar. So I'll have hundreds of heads and each of them will do it by itself. And see, another very important thing, that this is purely a neural network. A neural network, I do not create features. I do not tell head one, please look for semantics, head two, please look for grammar. But the neural network can figure out, where I should assign what responsibility. So that is the important thing about neural network, and that's one of the important differences between neural networks and machine learning. So I hope you're impressed with that. Anyway, I went through this. We had the normalization and the feed forward and the second normalization. So we went through that. And then what we started with a single word, and now the word understands its place in the whole corpus, what it actually stands for. So that is the end result of the training what we achieved. Okay. And then we took the mask method to train our final model. So I hid a word and asked him to predict it, and it predicted correctly. There is a training cycle, and then you see it paid attention to the words went and money. I think went and withdraw, not money. So it paid attention to these words, and it could figure out that this is actually the financial institution bank and not River Bank and things like that. Then I put a Hindi word, and I created the embeddings for that, and I had the embeddings of the English words, and then I could do a cosine similarity between them to figure out what is the Hindi query about, and I could find the correct English news items based on the query which I had input. So, right. So I've come to the end of our discussion for today. Should have is a short discussion, but I hope. But this is a very important discussion. I hope I've been able to convey the message regarding attention heads and how the transformers are working. So you have the first step in that, because these are going to be critical knowledge which we will utilize in the further discussions. Right? Any questions?
Right.
Can you go back to the transformer, the one picture that you shared in the slide, where we were doing some normalization and stuff? So
yeah.
Not the previous one. Still further down. I think there was some normalization we used to do, right? There was a phase where you added.
Yeah. I'll show you. Yeah. So
what? Any reason mathematically why we are doing this normalization? So what happened?
Yeah. Now it is the same concept. Like take your ordinary case. Supposing you're finding you're creating a model for predicting the price of a house, and you have data like square feet area and number of bedrooms. So these two data points, their significance values are much different, right? Square feet area will be in 4 digits, possibly, or 5 digits, and number of bedrooms will be in 1 digit or 2 digit. So if I put that into the model for making prediction, the square feet area will dominate. It will suppress the contribution of number of bedrooms. That is why we do standardization or normalization. You remember?
Yeah. I remember for the regressions and stuff that we used to do initially.
Yeah.
I was trying to find out why we do that here.
And it is the same concept. Now, what is happening is that so much of calculations which I'm doing, because of which the values that I'm generating, they will all become of different ranges. So what I do is that after doing intensive calculation, I will add a normalization step so that I bring the values in the same range, and then again proceed for the next step operation.
Okay, got it. Okay. So they don't blow up in values so that we can keep them under.
Not blow up. Blow up is not I'm concerned about, but I'm concerned about the fact that there should not be a very big disparity between all the values.
Okay.
In terms of its range.
Okay.
Right. Anything else?
Finally, last one. So you explicitly added the tag, right? You said in the BERT we can add any tag like CLS and then the CP or something in the end. What happens if I don't add it? So is it mandatory that I need to add? And
no, this is mandatory. Absolutely mandatory.
Okay.
What is this algorithm?
For that algorithm, okay. I can add any tag that I want, not necessarily to be CLS.
No. These are very specific.
Okay.
You cannot add anything and everything. See, When I initially trained my toy model, I explicitly showed you that I'm adding those tags. But when I trained the full model, I did not add those tags because BERT will add those tags.
Yes. So the what is the reason for? Because when I saw the attention head in the end, right? I saw the withdraw was higher probability with the softmax value, and then I saw CLS also having the next highest probability. Then came the event. So now that we have a CLS, so what does that mean actually?
Thing is that it says that the beginning of the sentence has more attention to the word. That is what the attention is finding out.
Okay.